So the last talk today is by Andrea, who will talk about some McEliece variants based on monomial codes and some cryptanalysis. Thank you.
Okay, so hello. Well, you already made introductions, so I'll start my presentation. For context and motivations, self-dual monomial codes are an active field of research, as you know, with various applications in cryptography. And my work with Dr. Vlad Dragoi focuses on self-dual codes with a monomial underlying structure and their application in code-based cryptography. Code-based encryption schemes based on linear codes are supposed to be quantum secure, with their security based on the general decoding problem of linear codes, which are supposed to be hard. And to establish the security of a scheme, a detailed analysis of the code family is necessary. Public key encryption schemes from codes, the best known is McEliece, which was already mentioned. I'll just give you a quick reminder of how it works. So we generate a family of codes with an efficient decoding algorithm where G is the generating matrix. Then in the key generation step, we take an invertible matrix S and the permutation matrix G, and then we multiply our generating matrix to the left and to the right with each of them respectively, and we get the generating matrix of the public code. And finally, in the encryption scheme, we multiply our message to the right with our public generating matrix, and we intentionally add an error, which we'll be able to find because our codes are error correcting. Our error has weight small enough. Right. So attacks for the McEliece are message recovery attacks, which is basically the general decoding problem, key recovery attacks, which can be reduced to the code equivalence problem, and distinguishers, which can tell our structured code apart from a random code. In summary, structured codes are supposed to be easy to decode, and then computing the public code from the structured codes is also supposed to be easy. Finding the structured code from the public code is the code equivalence problem. We don't know the difficulty of decoding the public code. Telling apart the public code from a random code makes use of distinguishers, and then decoding a random code is a hard problem. We're moving on to self-dual monomial codes. Examples of these are the Reed-Muller codes, polar codes, and also self-dual monomial codes are a special class related to decreasing monomial codes. As the first two examples have already been cryptanalyzed using sub-exponential or polynomial algorithms, we focus on the third example. Security arguments for these are as follows. We get no extra information from working in the dual space. Generic algorithms for the code equivalence problem, such as the support splitting algorithm, are impractical because of the large dimension of the whole and because the permutation group of the code is non-trivial. Moreover, the square code reveals no non-trivial information in general. And even in special cases, such as in the example where the code leaks information about the xi you see there, squaring and shortening still only reduces the problem to the most difficult instance of the code equivalence problem for Reed-Muller codes. And finally, the permutation group of a code generated by a monomial set I greatly varies with our monomial set, and so do the number and structure of minimum weight code words. Now we'll see what monomial codes are. Their ambient space is the ring of polynomials of degree in m variables, binary polynomials, quotiented such that squaring any of the variables equals the variable itself. To each such polynomial, we associate an evaluation function over all the elements of f2 to the m. And we define M index M, the set of all monomials. So Now, the monomial code generated by a monomial set I is the span over F2 of the evaluations of all the elements of our monomial set. I'll show you an example where m equals 3. So here we have all our binary words of length 3 arranged decreasingly. And then the evaluation of x0, x1, x2 is a vector with one only where all the binary digits are 1, because that's how they get multiplied to 1. Then the evaluation of x1, x2 is only one where the second and the last binary digit are 1. Then the evaluation of x0, x2 has coordinate 1 where the first and the last binary digits are 1. X2 is 1 where the last binary digit is 1, and so on for all the other monomials. The evaluation of 1 is basically the empty, say, monomial is 1 everywhere. If we delete the first 3 rows of this, we get the generating matrix of a polar code. And then if we also delete the 5th row, we get the generating matrix of a Reed-Muller code, which is self-dual. For structural properties of monomial codes, we remind the definition of a Schur product. Now, we know that if we evaluate, it results directly from the definition of the evaluation function, that two monomials evaluate orthogonal vectors if and only if the degree of their product is less than m. And we define the multiplicative complement of a monomial G by dividing the maximum degree monomial by G. By extension, we define the multiplicative complement of a set as the set of the multiplicative complements of the set's elements. Finally, a monomial code is weakly self-dual if for all f and g in the generating set, we have that their product it doesn't equal the monomial of maximum degree. And it is self-dual if it is weakly self-dual. And if taking all the monomials in the set and the monomials in its multiplicative complement, we cover the entire set of monomials. Now, I mentioned decreasing monomial sets earlier. We finally got to the to where we order the monomials. We have 2 orders, a weak one and a strong one. We say f is weakly less than g if f divides g. And then for the strong order, if 2 monomials have the same degree, we compare the first index. So the indices are arranged increasingly for each monomial. And then we compare the first index from the monomial on the left with the first index on the monomial on the right, and so on. So if each pair of monomials, one from the left and of indices, one from the left and one from the right, is ordered increasingly, then we say that the monomial on the left is less than the monomial on the right. And for different degrees, we say that f is less than g if and only if we can find the g star that divides g of the same degree as f, such that f is less than or equal to g star. I'll show you a representation of this pose set with the strong order for m equals 4. So the smallest monomial is 1. Then x0 is greater than 1. x1 is greater than x0. Then greater than x1 are both x0, x1, and x2, but x0, x1, and x2 are incomparable. Next, x0, x2 is greater than x0, x1, and then x2. And x3 is greater than x2, but x0, x2, and x3 are incomparable. And as follows, you can see by the arrows what is greater than what. Right, and finally, the greatest one is x0, x1, x2, x3, which is the monomial of maximum degree. Here we can see a decreasing set. So we have 1, x0, x1, x2, and x0, x1. And so the set generated, the code generated by this monomial set is a decreasing monomial code because the set is a decreasing set. We have classified self-dual monomial codes in two classes, each with two subclasses. Firstly, we split it into classes by whether all the monomials of degree less than or equal to m/2 - 1 are in the generating set. This is the first class, and then the second class when they are not. And for the first class, we have the case where all the monomials in our set J are divisible by one of the variables. And then the second class is when they are not. Whereas for the second class, we split it by whether there is monomial of degree 1, so one of the variables that isn't in the generating set. And the second subclass is where all the monomials of degree 1 are in the generating set. For our first class, we have written a construction algorithm inspired by the cited works. So we require an integer m and an I from 0 to m-1. And this algorithm gives a self-dual monomial code C of I. First, we let I be the all the monomials of degree less than or equal to m/2 - 1. And then we take basically all the monomials of degree m/2 and split them into two columns. On the first column, we put all the monomials that are divisible by an xi. And then on the in the second column, on each row, we write the multiplicative complement of the corresponding element in the first column. And for each row, we pick randomly a monomial from either column. In order to get specifically the one where xi divides all the elements in J, so that would be the first class, subclass of the first class, we would just take elements from all the elements from the first column for J. Next, we devised a key recovery attack for the case where all the elements of J are divisible by xi. This has already been published. So we require a public self-dual monomial code, and we ensure a permutation pi star such that the public code is the original code permuted by pi star if our generating set is as we desire, or error if not. This relies on the following theorem. If I is such that it contains all the monomials of a degree m less than or equal to m/2 - 1, then its square is a weakly decreasing monomial code, as you can see. This means that the dual of the square code has dimension 2 if all the elements of J are divisible by an xi, or dimension 1 otherwise. Returning to our algorithm, first we compute this this dual of the square that I mentioned. And if it has dimension 2, then there is an xi such that it divides all of the elements of J. We retrieve the code word, which is the evaluation of the permutation of this xi. So it's not the 0 vector nor the 1 vector. And we shorten our public code on the support of C. This gives us a code that is equivalent to a Reed-Muller of rank m/2 - 1 and size m-1. So if we solve the code equivalence problem, we get our permutation pi star. We have a theorem that we have proven a theorem that basically says that our algorithm works as we say it does, and also proves its overall complexity. Finally, this is yet unpublished work. This is a key recovery attack for the second class, where not all the monomials of degree less than or equal to m over 2 minus 1 are in the generating set, but all the monomials of degree 1 are there. So we require a public self-dual monomial code, and we ensure a pair of matrices P and Q such that the public code is the code generated by the inverse of Q multiplied by the block matrix with 2 identity matrices and P. If all the monomials of degree 1 are in I or error otherwise. So we retrieve all the code words of weight 2 from the code, and we see if there are 2 to the n minus 1 of them. If this is the case, then these code words form a basis for our code. So we put all the code words in as rows of our other matrix W2 and solve the matrix equivalence of W2 and the block matrix mentioned before. This returns our pair P and Q that we desire. Thank you very much for listening. Do you have any questions?
I have one myself to begin with. So earlier at the beginning, you mentioned about the properties of self-dual codes, and you talked about rightly like SSA being the hardest, etc. And then you mentioned something about the square code. Can you go back to the?
Oh, you mean?
Yes, the square code so reveal non-trivial information, and so are you aware of some of the impact of the square code on the code equivalence problem as well, or is this just strictly pertinent to the case of monomial codes?
I'm sorry, I couldn't hear the question very well.
Yeah, I will repeat. So when you talk about the square code revealing non-trivial information,
yes.
Are you aware of the impact of the square code for code equivalence problem as well, or is this strictly talking about?
Am I aware of the impact of the square code on what?
For the code equivalence problem, or is just
for the code equivalence problem? I am not entirely sure. So,
did you hear the question? Or?
Yeah, yes, I did. So what I said. This little bit here is the theorem over here, this one, where it does reveal some information. We focused on this particular case where xi divides all the monomials in J. We did look at the square code in the case where there is no variable that divides all the monomials in J, but couldn't find, so it doesn't reveal any information. It's more like we couldn't find that it reveals information.
Okay, yeah, I was just curious because you mentioned that this is the hardest code equivalence problem instance in this case, so I was just wondering.
Yes, because it's with the Reed-Muller of, so it's basically with Reed-Muller of rank m over 2 minus 1 and m minus 1. On the line where it says code equivalence problem. That's why I said that it's the hardest instance of the code equivalence problem with the Reed-Muller code.
Okay. No, if not, Thank you, Andrea, for the talk again.
Thank you very much.